So in the previous lesson, we built a logic which controls program counter. And now, generally, we have somewhat decent microcontroller which can do some things. For example, do some arithmetic operations on general purpose registers, send data out to random access memory, read uh, and write to random access memory, do the instructions and so on. And now what we need to do is just put this all together in some form of working device. So we have several blocks, and each of these blocks has control bits. And right now we have very many control signals. For example, we can select source of general purpose registers. We can select whether it's going to be value from flash, value from RAM, value from arithmetic logic unit, or value from status register. Then we have control signal for selecting address of register to output on lane A, and also into which register to write the value. So this is the same signal. It's used for both. Then we have select B signal, which selects which register is going to be output on general purpose register signal B lane. Then we also have signal which enables or disables writing to registers. We have arithmetic logic unit operation selection signal. We also have signal that enables or disables writing to status register. We have signal that selects flag for comparison and for program counter jumps. And, maybe it seems like this crazy amount of control signals in this microcontroller, and how the heck do we control them all in such a way that everything starts to work? So this is what we're going to do today. And actually, it might seem like a really complicated thing, but it can actually be done pretty simply. So the microcontroller has a special block, which is called instruction decoder. The instruction decoder receives instruction from the flash memory, and it it just sets up all control signals based on the incoming instruction. So, so we're going to implement instruction decoder, and it's going to actually be easier than you might think. So to implement instruction decoder, we're going to just create a table where we try to figure out all of the functions that our microcontroller has to do and all of the control signals that our microcontroller has. So let's just go through all of the possible things that microcontrollers can do. So you can go and look up some existing microcontrollers and check out their instruction set, and you'll see that all of these microcontrollers pretty much have the same basic functions that they support. So first of them is they can do arithmetics on registers. So this is why we build the arithmetic logic unit. So one of the instruction types is arithmetic logic unit instructions. These instructions include addition, subtraction, and so on. Next instructions that we have are compare instructions. So arithmetic logic unit instructions take values of two registers, for example, add them together and write back the result into the third register or one of the input registers. Compare instructions are used to compare two numbers. They, for example, subtract one number from another, but they don't write the result back into any registers. They just subtract them and set the status register flags. For example, if the numbers were equal, then 0 flag will be set. And so this is used like testing. So it's similar to arithmetic logic units, but it just doesn't write the result back into registers. So when we start programming, you'll see how it's used. Next instructions that are in all microcontrollers are LDI instruction. This instruction just loads a value into register. So you, for example, want register number 0 have value 5, you use LDI to load the value into register. Then we have some instructions to read from random access memory and write to random access memory, and they are called load from RAM and store to RAM. So I'll call them LDR and SDR. So load from RAM, you give an address in RAM, and the processor reads the value into a register that you say. And store does the same thing, that the opposite way. You give a register and an address in random access memory, and it writes the value of register into certain random access memory location. Then we also have jump instruction, which basically says jump to a new location in program. This is, for example, for your loops or function calls. You know, you want to do something, you jump to some other place in code, do it, and then jump back, for example. And then there's also branch instructions. Branch instructions uh, are for ifs. So it's like jump, just only if a certain flag in the status register is in certain value 1 or 0. So for example, you first do comparison between two registers, and then if, for example, 0 flag is set, then branch to a new location, else don't branch to a new location and keep doing the next instructions as if nothing happened. So these are our basic instructions. There are also more instructions in modern CPUs, but these are in all CPUs. These are kind of universal. Maybe their names are a little bit different, but they're just the same. So now let's figure out how we could, let's first write all our control signals. So what control signals do we have? We have, for example, general, we have, for example, general purpose register source select signal. It's 2 bits. GPR source select bit 1 and GPR source select bit number 0. Okay. Another control signal is, for example, address for A and for writing. So control signal, address for A and writing, and address for B and writing. What we are going to do is we are going to construct our instructions in such way that we will use 16 bits for each instruction, 16-bit instructions. And we'll just divide them in 4 nibbles. Each nibble is 4 bits. So here is 4 bits. Here is another 4 bits. Here is another 4 bits. And here is another 4 bits. And since we have only 8 registers and our CPU only has 16 bytes of RAM and 256 bytes of flash memory, we can divide the instruction in certain parts, and each part is used to control certain signals in our CPU. So for example, let's say that first 4 bits tell us what instruction we want to use: arithmetic logic unit instruction, or comparison instruction, or LDI, LDR, store, jump, branch. So these 4 bits is instruction or opcode, or just instruction. Next 4 bits, let's use to directly control address of A, general purpose register A, and for writing. So these 4 bits, well, actually only 3 of them, and fourth bit will be just 0. Bottom 3 bits of this 4-bit nibble are just going to be directly connected here to address A and writing. So this will be our destination register. This is called destination register because it's used as an input and also as the location to which to write the result. Okay, this controls address A and address for writing in general purpose register. Next 4 bits, we will, for example, connect directly to arithmetic logic unit operation selector. And then with these bits in our machine code, we can control what arithmetic logic unit operation we want to do. So I'll just write it here, alu cell. And the last 4 bits we will use, for example, for address B. So this is called source register, RS. I'll center these so that it's easier to read. So source register, because it is taken into arithmetic logic unit through lane B, but we write back to register A, not B, so it's like a source of information, but this register A is source and destination for the operation, so it's called destination, and this is source. So this will be register for destination. Basically, it's going to be register A. A lane, and source will be B lane. Okay, next, this would be for arithmetic logic unit operations. So the first 4 bits will be just some code for arithmetic logic unit. Then next 4 bits will be one register. Next is operation selection, and next bits for destination. Sorry, for source. Actually, maybe I can just put it right here, because different instructions will have different meanings. So I will put them right here, like this. We have comparison function as well. So difference between arithmetic logic unit and comparison is just that destination is not overwritten. It's read, register B is read, but the result is not overwritten. So now now I'll write all control signals, but I'll skip the signals that are encoded already in the instruction word. So control signals, for example, general purpose register source select here. It's not controlled directly with some bits of the word, so they're like a separate thing. Okay, next control signal that we have is write enable general purpose register. So write enable general purpose register. And let's just start writing the values of these control signals for arithmetic logic unit instruction. So if we want to do arithmetic logic unit instruction, first question is, do we enable writing a result to destination register? Yes, we want to enable it, so this bit will be equal to 1. And for general purpose register source select, we look at this multiplexer. This is what controls from which we want to read, from which inputs we want to read and write to the register. So for arithmetic logic unit, we select 2 registers, we do some calculations, and we want the result to be written into registers. So this multiplexer should not select value from flash or value from RAM. We need that it selects value from arithmetic logic unit, which is 0, 1, 2, to input number 2 of this multiplexer. So source select bit number 1 is 1 and bit number 2 is 0. And I will center these as well so that it's clear. So general purpose register source select for arithmetic logic unit instructions is 1, 0. Write enable signal is high. We want to write the result into destination. Let's check out what other signals we have. Arithmetic logic unit operation selection is already determined by the instruction and read directly from the instruction, so we don't touch that. Then we have status register write enable bit. So when we do arithmetic logic unit instructions, of course, we want the status register to be updated with the new flags. So we do some arithmetic logic unit instruction, result is 0, so we want 0 flag to be set. So status register write enable signal needs to be high. It needs to be 1, okay? So that the flags are updated. Then what else do we have? We have so this part is for jump instructions. We will not touch it yet, but what we know is that we can control this enable jump or branch. We want it to be 0 because arithmetic logic unit instruction has nothing to do with jumping around the code, so enable jump will be 0. So this is control signal enable jump branch, and its value is going to be 0. We want it to be off. We want that when we do arithmetic logic unit instruction, program counter just increments by 1. We don't want to jump after arithmetic logic unit instructions. So program counter is just going to be incremented by 1 position, and it will just move to the next line in our code. So that's it. So force jump, flag compare, and flag select, we will not touch yet. We will configure them later. And actually, if we look at this, there aren't any more very much signals to control. So let's just leave it at this point. So let's check out the next instruction, which is compare. So to not mix everything up and to not make different bits in different instructions, the same bits in different instructions to mean different things, we will just reuse these bit positions from arithmetic logic unit also in comparison instructions. So basically, first 4 bits will be instruction name. Next 4 bits we will use for comparison register A selection. So this will be the same. Next 4 bits we will use for arithmetic logic unit instruction selection. So for example, if you want to compare 2 numbers, we will select instruction with the name subtract. So we select 2 registers. If we subtract them and the result is greater than 0, then we know that the first number was bigger. If it's, for example, equal to 0, then 0 flag will be set, and we know that these numbers were equal, and so on. And with comparison, we can also do some bit checking using AND instruction. So this we will just leave the same. When we start programming in assembly, you will understand the usage of this. So I'll just leave it to that. Next, when we use comparison, we want to read the registers and do the arithmetic logic unit instruction, but we don't want to write the result back into destination register. We just want to compare something and not to overwrite. So when we select the source of, well, let's first deal with this write enable general purpose register bit. So since we only want to touch these numbers and not to override them, we just set write enable to 0. And at this moment, writing to general purpose register is disabled. So the register original values are safe. They will not be overwritten. In that case, selection of input for general purpose register doesn't make any difference because the value will not be written into general purpose register. So these bits are actually so-called don't care bits. We can set any value for general purpose register source select. Since writing is disabled, it doesn't matter where the input comes from. These bits have to have some value, but it doesn't matter what value it is. Next, do we want to enable writing to status register? Yes, we want, because if we don't, then the flags will not be updated and we will not know the result of the comparison. So we want to turn on status register updates, but we don't want to enable writing to the registers. And then, do we want to enable jumping? No, so this is off. Next instruction is LDI instruction. So the first 4 bits will be some kind of code for LDI, which will be just instruction code. Then, since we use these 4 bits to select address of register to which we want to write, register A, then of course, we will not deliberately put these 4 bits someplace else, and we will just leave them in the same second nibble of this number. So destination register A will be encoded in these 4 bits. And as I mentioned, since we have 8 registers, so the first bit will be 0, and then the number of register 3 bits, something like that. So and next, we have 8-bit processor. So with LDI instruction, we need to be able to load 8-bit value into this register. And look at this, we have exactly 8 bits free, which we can use for this number. So these two nibbles are just kind of washed together, and this will have this value k. So constants in assembly documentation are usually just called k, and this is where the number will be encoded. And check out, you might think that, well, there's some conflict because in one instruction these 8 bits are used for arithmetic logic unit selection and for register B selection, and in another instruction they are used for some number storage. But just bear with me, we will disable usage of register B and arithmetic logic unit with these control bits. So for LDI instruction, first let's deal with general purpose register source select bits, with which we select what from which place do we copy value into the destination register. This is this multiplexer which has value from flash, value from RAM, value from arithmetic logic unit, or value from status register. And in this case, to load some constant value, which is encoded in the instruction which comes from flash, we will just use the input number 0, which is a value from flash. It's not going to be from any location from flash, just from the instruction that we are currently executing, but it's still from flash. So this will be input number 0. So general purpose register source select bits are 0 and 0. Next question, do we want to enable writing to general purpose register? Yes, because otherwise this number will not be written into the register. Next, do we want to update status register? Since this is not an arithmetic logic or comparison instruction, we just switch off updates of status register, and this way status register doesn't get overwritten. It's just frozen, its writing is stopped, and nobody can write to it, so it's just gonna stay the same. Then, do we want to enable jumps? No. So currently this is very boring signal, it's just always 0. It will be 1 only on jump and branch instructions. So check this out. When we select source from flash, then we don't really care what bits are set for arithmetic logic unit operation selection or input B. even though these signals are connected to arithmetic logic unit and it will calculate something, since in this multiplexer we are not using this signal, well, it's just going to stop here. It's just going to show some value, but it's not going to break the CPU because we're selecting different input for general purpose register. And also for status register, even though the same bits in K will select arithmetic logic unit operation and register B, and they will calculate something and also will show some flags, since writing to status register is switched off, nothing will happen here. And so basically we can reuse the same bits for different things as long as they don't overlap in the same instruction. And by control signals, we make sure that nothing is being damaged or overwritten. So this instruction construction will be like this. Next instruction is load from RAM. So first for nibbles, we'll say the instruction name, for example, encoded with some binary code for bits. And then we need to load from RAM. Loading from RAM is the same as loading from flash, just in this general purpose register source select. Instead of input 0, we want to use input 1, which we will connect later to random access memory. Load value from RAM. So basically, let's just reuse the same bits. Destination register is in these 4 bits, and they are hardwired to this control signal. And the next 8 bits, okay, in this case, we have flash memory, random access memory, which is only 16 bits, but we can have up to 256 bits. In our example CPU, I deliberately made it 16 bits, so 16 bytes, so that I can show you stack overflow and also that random access memory fits in one screen. So in this case, the top 4 bits of the bottom byte will be just 0, and the bottom 4 bits will be address in RAM. So that means the following: the bottom 4 bits from instruction will be just directly connected to a signal which we actually have not created yet, but I'll create it now. This will be output, and I will call it address RAM, address in random access memory. Number of bits is going to be 4, 2 to the power 416, and we will just connect this line directly to the bottom 4 bits of our instruction. Okay, and this way we can just select which address we want to touch. And so now let's fill in these control signals. General purpose register source select is source number 0, 1. So top bit 0, bottom bit is 1. Now, do we want to write to general purpose register? Yes, so we enable writing. Do we want to update status register? No. Do we want to enable jumps and branches? No. And so by connecting bottom 4 bits, not only to source register control, but also connecting them to address RAM, we will be able to perform the action. Actually, I can connect them right away. So this is address B. And basically, I just connect it directly to address for random access memory. Oh, these are 4 bits and these are 3 bits. So it will be a little bit more sophisticated. I'll do it in the instruction decoder. We'll just add 1 0 for address B. And then it will work. So next instruction is store to random access memory. Instruction code. Let's just reuse the same bits. These 4 bits from instruction directly connect to A. And then next 4 bits will be again 0, and next 4 bits will be address in RAM. Okay, I'll call it like this. And now what are the control signals? So since we want to read from general purpose register and write its values somewhere out, we don't care what the general purpose register source select signals are, because we don't write to the general purpose register source. Source can be anything. So these we will just replace by, for example, zeros later. Then do we want to enable writing to general purpose register? No. So this signal is 0 because we want to read from it and write to RAM. And then we have status register write enable is 0, enable jump and branch also 0. So what we want to do is write to random access memory. So these 4 bits, bottom 4 bits select the address, top 4 bits select destination register from which to write to random access memory. So we need to add one more signal, which is data to RAM, data to random access memory. And it's going to be 8 bits. So we can send one register, which is 8 bits, data to RAM. And since we select lane A as the source of information, then we just connect this lane directly to data to RAM. So basically, when I select register, for example, inside general purpose register, register number 2, I write some data, for example, 55. In the CPU, when I select address number 2, register number 2, its value is fed into arithmetic logic unit, but it's also fed to data to random access memory. So with the same bits, we can select both, so we don't have to create new bits for every combination of instructions. So it works like this. To make sure that this data, for example, in arithmetic logic unit instruction, is not used for arithmetics and also at the same time accidentally written to random access memory, there are 2 more control signals for random access memory, which are enable writing to RAM. So I'll call them write to, or better, let's just use consistently, write enable random access memory. So when this signal is low, random access memory is locked, protected from accidentally writing to it. We can read from it, but we cannot write to it. And another signal that we will use in this implementation will be read enable from random access memory, because there is special signal in the Logisims built in random access memory block, which you set it high to read from random access memory. So we will just put it. Maybe it's a little bit useless, but we just have to use it. So let's create these 2 control signals in our table. So write enable RAM and read enable RAM. So, and I can just fill these pretty easily. In instructions that are comparisons, LDIs, and so on, we want write enable to be 0. And we want write enable to random access memory be 1 only when we store something into random access memory. So I set 1 here. Then for reading from RAM, all the time is 0. Only when we want to read from RAM some value, we set it high. And for the rest of the time, it's just going to be off. 0. So these are control bits for writing to random access memory. Next instruction is jump. And jump instruction requires one parameter, which is address to which to jump. So it basically just forces program counter equal to some address. So in order to tell which address, we need to encode that address into our instruction word. And since we're using these 4 bits to select an 8-bit number, so without really much thinking, let's just use the same for 8 bits to also use for address selection. Jump address. Okay. And these, for example, bits we will just not use. It's 4 zeros, for example. They're just not used. Now, when we have jump instruction, general purpose register source select bits are don't care. We don't care what their value is because we are not writing to general purpose register. Write enable to general purpose register is 0 because we don't want to write anything to it. Status register write enable is off. Enable jump branch is on. Now we set it to true. Then write enable to RAM is 0 and read from RAM is also 0. We don't want to do it. And now we can check out this bottom part, which is force jump or not. So there is force jump, which distinguishes between jump and branch. So when we set this high, it will definitely jump. So there is this control signal called force jump. And it is true for jump instruction. For other instructions, it's just 0. Or better thing to say is that it's actually don't care. It doesn't matter what its value is because we have disabled jump with a different signal. So it doesn't matter if it's 0 or 1. So right now I just write x's. But in reality, at the end, we're just going to replace all x's with zeros. I'm just saying that since we have disabled something someplace else, this bit doesn't play any role because its signal is being cut off. So this is for jumping, and jump address is here. So we will just connect these instead of this control signal. We'll just connect it to the bottom 8 bits of our instruction, and it's going to be fed into program counter when we want to jump. Next, we have branch instructions. So instruction for branch. So branch is the same as jump, just with some condition. And let's try to figure out how we can encode it in 16 bits. So let's reuse the jump address bits from jump. So I'll just call them, well, I'll call it the branch address address to which to jump if the condition is true. And now let's check out the conditions. So for branch instructions, we have 4 flags. We have flags 0, negativity, carry, and signed overflow. And I will write them in correct order so that there's no confusion. So in our arithmetic logic unit, the flags are V, N, Z, C. So I'll just write them like this: V, N, Z, C. V, N, Z, and C. And here, their order is 0. So this is bit 3, 2, 1, 0. So carry bit is bit number 0, 0 bit is bit number 1, negativity is bit number 2, and signed overflow bit is bit number 3. So we have 4 flags. So we can select between them using 2 bits. And actually we have these 2 bits, flag select bits. So we have flag select bits with which we select between these 4 flags. And then we can compare the flag value with 1 or with 0. So we can have branch if 0 set or branch if 0 clear, branch if carry set or branch if carry clear. So we basically can compare with 1 or 0. Compare the flag with 1 and 0, 1 or 0. And we have this control signal, which is called flag compare. So basically, status register flag number 0 is set, we select 0, and then we compare it with 0. So it's set, it's 1, we compare it with 0, so it returns false, or we compare it with 1, it's 1, compared with 1 gives true, so it's 1 output. So this way we can have the following branch instructions. Branch if 0 set, branch if 0 clear, branch if carry set, branch if carry clear, branch if negativity flag set, branch if negativity flag clear, branch if signed overflow set, and branch if overflow signed overflow clear. So we have 8 combinations, and here in these 4 bits we can have up to 16 different combinations. So actually, instead of creating new control signals here, we can just use these 4 bits to control the comparison 1 or 0 bit and flag selection bits. So what we are going to do is we are going to locate these bits in the following manner. We will encode them in the following manner. Since we have 8 combinations, then top bit will be don't care. So for example, X. Then the next bit in these 4 bits is going to be the value to which we compare. So value bit. And then the next 2 bits will select flag selection bits. And then we don't need to create a new column here. So basically these 4 bits, top one of which is going to be 0, the next we will just directly connect to our Logisim flag compare. We'll just directly connect it to the instruction word. And the next 2 bits we will just directly connect to flag selection. Okay. And now let's fill in this table for branch instruction. So general purpose register source select bits don't care. Write enable general purpose register. We don't want to enable writing to it. Status register update disabled. Enable jump or branch. Yes, enable. Write to RAM off. Read from RAM off. Force jump. So in this logic, basically, if force jump is true, then we will always branch. If it's off, then we will only branch if value that we compare is equal to flag's actual real value. So force jump is off, but flag compare and flag select will determine whether we jump or not. But these are not separate flag control signals because we will just take them from the instruction word. So we don't create a new column here. We just have to remember to connect them. And basically this is our table. First jump, enable jump, update such register, update general purpose register, source, write RAM, read from RAM address source. Okay, and generally that's it. So we have these instructions and we have these values for control signals. Now the question is, how do we, determine the values? How do we connect them? How do we manage all of this? So what we could do, which would be the hard way, is we first give each of these instructions a code, which is different from any other instruction, and the easiest way is to just enumerate them. So arithmetic logic unit will be just 0x00. The first 4 bits will just be 00. Comparison will be, for example, 0x01. LDI will be 0x02. Sorry, this is just 4 bits, so 0x1, 0x2, 0x, oh, sorry, 0x0. 0x1, 0x2, 0x3, or in decimal because they match, but later if we have more instructions, they become A, B, and C. So I'll just write in hex 0x4, 0x5, 0x6. So basically, these will be the code names for instructions, each code name 4 bits. And then what we could do the hard way would be we take 4 input bits and then create truth tables for each control signal, and then we make them from NAND and NOR elements. And of course, it would be very time consuming. But guess what? There's an easier way to do it. And we can actually do it using a lookup table. We can use small read-only memory, which has address signal this, and data output is just direct combination of these ones and zeros. So how many bits we have? 1, 2, 3, 4, 5, 6, 7, 8. So actually we can make a small 8-byte read-only memory, like a flash memory, like a lookup table. And when we say 0, it outputs us 1, 0, 1, 1, 0, 0, 0, 0. When we say 1, it returns us 0, 0, 0, 1, 0, 0, 0, 0. When we say 5, it outputs 0, 0, 0, 0, 1, 0, 0, 1. Get it? Get the idea? So we can just use a lookup table, and we can actually solve this instruction decoder mystery very easily. First thing that I'll do, just to clear it up, all x's I'll just replace by zeros. I'm just showing you that these are don't care bits because they are switched off by some other bits. But now that we are trying to create some real read-only memory, I'll just write all zeros to the x's. So x 0, 0, 0, 0, 0, 0 here, and 0, 0, 0. Okay, and now I'll just write these values in hexadecimal format. Full control word, full control byte. So 0, so 1, 0, 1, 1, using a calculator, is hexadecimal B. I'll write in hexadecimal because that's how Logisim accepts these values. 0xb, and 0, 0, 0, 0 is just 0. 1, 0, 1, 1. Okay. Next is 0, 0, 0, 1, which is 1. 0, 0, 0, 0 is just 0. 0, 0, 1, 0 is 2. 0, 0, 0, 0 is just 0. 0, 1, 1, 0 is 6. And 0, 0, 1, 0 is 2. 0, 0, 0, 0 is 0. And 0, 1, 0, 0 is 4. 0, 0, 0, 0 is 0. And 1, 0, 0, 1 is 9. 0, 0, 0, 0 is 0. 1, 0, 0, 0 is 8. So we just make a black box to which we say instruction code, and it outputs us all of these control signals bundled in a single byte. And then using a wire splitter, we'll just split it into bits, and we're just going to output these bits to each control signal. Okay. So actually, using this lookup table, we can solve this instruction decoder mystery very easily. Okay, so now let's try to build instruction decoder as a separate block. We don't want to make this into a cable jungle, so just new circuit. So project add circuit. We will call the circuit instruction decoder, and let's try to build it. So basically what it consists of is just a lookup table read-only memory. So we place memory, read-only memory right here. Address bit width is just 4 bits. So we can select between only 16. Oh, wait a second. We can even have it just 3 bits. Okay, I'll leave it to 4 bits for now, because if we want to add more instructions, then we will have more operation code, these values, and so let's just leave it to this. Yes, so it just connects directly there. And data bit width out is 8. And so here will be the input. The input will be 4 bits, data bits 4. You know what? The easiest way to build it is that we take all 8 bits and we also distribute the rest of the bits to other locations. So actually, what we have as an input for instruction decoder will be full 16-bit instruction. So we select 16 bits as the input. The label will be instruction. So instruction comes in. Then we use a splitter to split this into bits. Let's see, fan out is 16 and bit within is also 16. So we just take the instruction and just distribute it per bits. Then it will be facing, for example, east. Yeah, let's have it like this. And then I connect it. Okay, so when I select this top bit high, this bit number 15 highlights. So basically the instruction word is top 4 bits, the instruction name. So I use a splitter. I select bit width in and fan out 4. And then I just take the top 4 bits, bit number 15, 14, 13, and 12, and I use these to feed into this read-only memory, this lookup table. And with these top 4 bits, I select which output to put on data. And this will be the full code of these control signals. And now I just need to write into this read-only memory these codes. So if instruction is instruction number 0, top 4 bits 0, then please output B0. So I click here and I type B0 and it's right there. So if instruction is instruction number 1, please output 0x10. So I just write 10. If instruction is number 2, please output 20. So I select 2, and in this location, I write 20. Actually, I don't have to, select it. I can just click on this entry and just write it in. So the next place is 62. The next one is 04. The next one is 09. And the next one is 08. So like this. And then when we read the instructions, the top part of the instruction will just select which control word to put out. And then I use a splitter. I rotate it to point east. Then I select fan out is 8 and bit data width in is also 8. And I connect them here. And now I can just create outputs for each control signal. So here I'll just enumerate them. So this is bit number 0, this is bit number 1. Sorry, the opposite direction. So this is bit number 0, 1, 2, 3, 4, 5, 6, and 7. And so force jump is bit number 0. So I just create an output. I name it force jump. And I connect it to bit number 0. So right now it's 0, but if I select operation jump, which is 5, then as you can see, operation selection with top 4 bits selects a read-only memory lookup table value 09, which sets force jump high. And then I'll just put this in the CPU and connect this output to force jump, and it will automatically do it. Next signal is read enable read-only memory, random access memory, sorry, is 1 bit. So I created so it's read enable random access memory, and it is controlled by the next bit. Next is write enable read random access memory. So here is write enable random access memory. Next is enable jump branch. I'll just use copying, it's a little bit faster. Enable jump branch is done by the next bit. And as you can see, I selected instruction number jump, which is 5. And through this lookup table, it outputs 9, which says force jump high, enable jump branch also high. And this is how we can control these things. Next bit is status register write enable. Sorry, I'll name it the same as in the CPU. So it's called reg write enable. I'll just name it the same here. It's the next bit in our decoded control signals. Next is write enable general purpose register. And the next 2 bits is general purpose register source select 1 and 0. And I could create two 1-bit outputs, but I'll make one 2-bit output, and I'll just use wire to mix these signals together. So label is general purpose register source select. I select that it's 2 data bits. I will use wire splitter to connect them, to mix them together. And I'll just check out that these bits are not mixed in the opposite direction. So let's see, I have instruction arithmetic logic unit, which is 0, 0, 0, 0. So it says general purpose register source select 1, 0, 1, 0. So it's in the correct order. As you can see, by selecting instruction 0, in the lookup table, it says control signal should be B0, which split into bits basically says force jump equal to 0, read enable from RAM 0, write enable to RAM 0, enable jump branch off, status register write enable true, write enable to general purpose register also true, and source to general purpose register is 1, 0, which is result from arithmetic logic unit, exactly what we need. So this is the core of instruction decoder. You might initially have thought, oh my God, this will be so complicated. You know, all of these control signals, how do we manage them? Actually pretty easy. Top 4 bits, just use lookup table and output these bits right away, this small read-only memory. So let's check out the next control signals that we have. So next 4 bits in our instruction will be register A selection. So in this instruction decoder, I'll just also manage them. So it's so that the main view would be as simple as possible. I take a splitter. I select the bits in are for so actually, I only need 3 bits here because destination register is 3 bits and branch instruction also. So actually, I use 3 bits and 3 bits here. So I just take this, I create an output, which I will call register A. This thing has data bit with 3, and so that I have enough space for these cables, this thing connects here. Next bit connects here. Sorry. Bit number 10 is not used in this case. So bit number 0, 1, 2, 3, 4, 5, 6, 7, 8. Bit number 8 is connected to bit number 0. Bit number 9 is connected here. Oops. Oh, sorry. Yeah, the lines are still a little bit off. So bit number 10, bit number is 11 is not used. Bit number 10 goes to bit number 2 here. Bit number 8 goes there. And this bit goes there. So now let's just test it. I select some register number 7 and it outputs number 7 here. So instruction word, if these 3 bits are set, for example, 111, then the register number 111, which is 7, is selected. Basically, this thing just copies these bits, and we just create a beautiful output here. Okay, so this is done. Next, we can also use these same bits to control this value comparison bit and flag select bits. So let's do exactly that. So I create output for this instruction decoder. Label is going to be flag select. It is going to be 2 bits. I will use a splitter, and I'll just steal from this place, and just be careful not to put them so that they accidentally connect there, or, you know, for clarity, maybe I just connect them here. I steal, sorry, I think it's like this. So, okay, so flag select bits are bits number 0 and 1 in this nibble. So when I set the bottom 2 bits high, then flag select is 1, 1. So it works correctly like this. So bit number 8 is connected to flag select 0, and bit number 9 is connected to flag select number 1. And next output is value to which to compare. So it's again another output, which I will name flag compare, I think was the name. Flag compare. Flag compare. And this bit, so I will move them a little bit like this. This bit is just taken from bit, is the same as bit number 2 in register A selection, which is just inside the instruction word, bit number 3 in the third nibble. So if I set this high, flag select compare is flag compare is set high. If I set it 0, it's 0. So this bit controls that as well. Okay. Next is jump address or a constant or branch address. Basically 8 bits are used. So what we can do is we can just bundle these 8 bits together and create an output which we will call, for example, bottom 8, and we will connect it either to program counter or to source of arithmetic logic, source of general purpose register multiplexer. So I create an output here. Its data bits are 8. Its output will be named bottom 8. And this will be used for, you know, many purposes. So splitter, we will use a splitter which has bits number in 8, and here also 8, and then I can put it here and just directly connect these together. This is how I get all 8 bits bundled up and connected to bottom 8. So with this method, when I connect this, for example, to general purpose register input, if I have number 3 in the bottom 8 bits, then number 3 is forwarded out and can be written to program counter or to register or something like that. And at the same time, these 4 bits, top 4 bits of this bottom byte are used for arithmetic logic unit select. So I create output called arithmetic logic unit op select. 8 is 4 bytes. And what I will do is I'll use a splitter, which splits 4 bits. And we will just connect them to the top 8 bits, the top 4 bits of the bottom 8 bits to the second nibble. So like this. So when these bits say operation 1, 1, 1, 1, then operation selector shows 1, 1, 1, 1. So this works correctly. And final signal is bottom 4 bits, which we use to select register B or random access memory address bottom 4 bits. So I use a splitter with 4 bits in and 4 bits out. I create an output which I will call bottom 4. Yes, this is data bits 4. And I connect it to the bottom 4 bits of instruction very carefully, not to mix up the bits. And that output can be directly connected to select B in general purpose register or address for random access memory. So let's check it out. If I change these bottom 4 bits to all ones, they all set to 1. So like this. And actually that is all of the instruction decoder. It takes in instruction from flash memory and it just forwards the bits to the corresponding locations inside the CPU. It sets all control values from lookup table, and it also forwards the bits to the corresponding locations in controls. So now I want to create some schematic element, a subcircuit from this. So I go into edit viewed circuits, subcircuit appearance. And here it is, it's just a box. Input is the instruction and the outputs are all of the instruction control bits. So actually, let's just leave it as is. Let's not rearrange them. Yes, and let's just put it inside our CPU. So this is instruction decoder. The only thing that I will do is I'll just put text ID, which is instruction decoder. So that we know the name of this block, ID. So I go to CPU, I click once on instruction decoder, I move it into this area, and here we have it. And I can just directly connect these outputs, which when I hover, they show the output name. I can just connect them to the control signals here, and everything will probably start to work. I will just add one more thing, which is called instruction register. So the flash memory is not directly connected to instruction decoder. It is first latched into instruction register so that during the calculations, the value doesn't, wobble around. So I select memory, register, And this register is 16 bits because each instruction is 16 bits. And the name for it is instruction register, IR. And so actually the flash memory connects here. So let's see. It requires constant enable. I'll just copy it from here. Enable always true. Let's just have it enabled all the time. Clock will be connected to clock. Reset will be connected to reset. So these I'll update later. And here I will put an input with 16 bits, which is from flash memory. So this will be flash data. So this is the place where we connect flash memory data output, and it first goes into instruction register, and this value is latched only on the rising edge of the clock, because if we just used it unclocked, then there could be some noise changes and something like that, and it could just swap the bits. So basically we first receive the data from flash memory, and then we connect it directly to the instruction decoder. Oopsie. Like this. And then what we need to do is just connect all instruction decoder signals to the corresponding locations in the CPU. So let's just start. So here, bottom 4 bits. If we look at our Excel sheet, bottom 4 bits connect directly to B selector, so address B, except it's 4 bits. So we would need to only use 3 bits of it. Yeah, okay. So we'll edit the instruction decoder a little bit. So instead of bottom 4, we will call it address RAM. So this is 4 bits, and we will just have to use another splitter to use only bottom 3 bits because the register selector is 3 bits. So I create a new output. I call it register B. It is 3 bits, and I take wiring splitter. This bits out 3 bits in 3. And I connect this here, here, and here. So register B is just bottom 3 bits. Okay. Instruction decoder like this. And then I need to increase its size like this. So I go back to CPU. It is updated, I think. And here it says address RAM. Sorry. I'll put it in once more. It put the register B at the bottom, so I'll edit that as well. So address B was put here, so I'll put it in top so that it's the same order that we have there, so there's no confusion, like this. Okay, I go to CPU. Now it says register B. Okay, so it's like this. So I just delete this address B, our dummy signal, and I just take it and connect directly to instruction decoder register B. And actually I can move it like this. Next output is address for random access memory, which is located here. To make the wires cross less, I will move it a little bit up. And I take this signal and I run it here. So from instruction register, these 4 bits will be taken to random access memory. Next is arithmetic logic unit operation selector. So I delete this signal, and instead of it, I just connect it to the next output. Next is bottom 8 bits. Bottom 8 bits are used as a constant for LDI instruction. So it's a value from flash. Here is value from flash. I delete it. And I take this signal and I connect it to instruction decoder so that bottom 8 bits will be written to general purpose register at the appropriate instruction. And also bottom 8 bits are used for jump address and branch address, which is here, new program counter value. So instead of some random value, I will run a wire which connects also here. So these bottom 8 bits are used for constant to be written into general purpose register, or for program counter new address for jump and branch instructions. Okay, next output is flag select. So it's located here. So I just delete it, and now I need to connect it. And now, of course, the cabling becomes a little bit crazy, but let's just, let's just try to do it. This is flag select. Next is flag compare, which is located right here. I delete it as well. Okay, maybe I'll put that wire a little bit differently. Flag compare and delete. Force jump will also be deleted. So flag select, flag compare. Like this. So flag select is this, and flag compare is the next signal here. Next is register A. So I delete it here, and register A goes straight here. Next is force jump, which was this control signal. So force jump goes here, here, and here. Next signal is read enable from RAM. To not make this thing really like a rat nest, I'll put these 2 signals here, and I'll just rotate them facing east. So write enable random access memory. I will put like this. And next signal is, sorry, this signal was read enable from random access memory. And next is write enable to random access memory, like this. Next output is enable jump and branch, which is here. So I delete it, I take the signal, and I run it here. And probably to make less cables, I can rotate this thing facing south. Oops. Select is top right. So like this. Then I can directly connect it. So, and it comes from the top. Next control signal is status register write enable. It's right here. So I connect it there. Next control signal is write enable general purpose register. It's right here. Next and final control signal is general purpose register source select. So I connect it like this. Okay. And that's about it. This is our instruction decoder. And to just check out if it works or not, let's create some instruction and let's check out if it works or not. So we will create instruction with which we want to, for example, load a value into register. So LDI first 4 bits are 2. So first, I'll write it in these windows. So LDI instruction is instruction number 2. Register to which we want to write. Let's say we want to write to register number 5. Then, and the value that we want to write is, for example, 120. 120 is sorry, in decimal 120 is hexadecimal 7 8. So this will be 7 and this will be 8. And now let's create an instruction which is basically 2 5 7 8. And let's see if the instruction decoder works correctly. So the instruction is 2 5 7 and 8. So 2 is 0 0 1 0, 5, so it's 0 0 1 0. 5 is 0 1 0 1, 7 is 0 1 1 1, and 8 is 1 0 0 0. So if the instruction machine code is 0 0 1 0, 0 0 1 0, and next is 0 1 0 1, and next is 0 1 1 1, and next is 1 0 0 0, then this is our word. It is not yet forwarded to the CPU. It is only read on the rising edge of the clock. So actually we need a clock signal. CPU. So I will create a signal which I will call clock. It will be a little bit different than this clock, so bear with me right now. So basically this clock connects to the clock. And when I do the rising edge of this clock, as you can see, instruction register updated, it read the instruction. So instruction photography happens on the rising edge of the clock. And when I switch the clock off, I can change these bits, but the instruction doesn't change. So when we move to the next instruction, there is no some random noise caused ones and zeros and CPU goes crazy because the flash data is buffered. And let's see, instruction register, instruction says that, you know, we created it as LDI, some number into register, and let's see how the instruction decoder used our data. So First is the important data, the LDI instruction. So first was register number 5 selected. I click on the um, register A selection signal. When I click on it, it says 5. So it took 5 and just forwarded it to general purpose register. So register number 5 is selected. Next signal is uh, is, for example, write enable on or off. Where is write enable? Write enable is off, so there is some mistake in our code because it should be set to 1. Let's see where is the mistake. Write enable is 1, 0, 0, 1, 0. Okay. So let's see instruction decoder. Oh, maybe the instruction decoder was actually lost the information when I edited it. So yeah, let's save this file, then go into instruction decoder. And since I did changes here, I think it deleted the contents. So let's just write the contents right now. So B0, next is 10, next is 20. It shouldn't have forgotten the values. So 62, 04, 09, and 08, like this. And now I go to the CPU and it updated. And now, yes, so it says sets the general purpose register write enable high. So writing will happen. Writing will happen into register number 5, bottom 8 bits. Let's find the output bottom 8. Bottom 8 is here, this line. So when I click on it, it says 120, which is the number that we want to write into the register. Then this multiplexer signal is set to 0. So input number 0 is forwarded into general purpose register. This number 120 is forwarded here. And what is also important, all the other signals are off. For example, status register write enable is off. Reading to RAM and writing to RAM and reading from RAM is also off. This is what instruction decoder did. Also, program counter will be incremented by 1. Jumping is switched off. Branching is switched off. Everything switch off. Just writing to general purpose register from flash bottom 8 bits is on. And when so right now the value is, so it comes in and it says 5, 5. Write is on. Okay, and address is, oh, so this is old value 5, 5. This is what I wrote manually previously. So on the rising edge of general purpose register, the value that was presented to general purpose register block is written into the selected register. So register number 5 was selected, so only its write enable signal was high, and on rising edge of the clock, register value was updated. And what we can make up for this is that, as I mentioned before, reading of instruction happens on the rising edge of the CPU, and writing happens on the falling edge. So basically what we can do right now is we can change this clock to the inverted version of this master clock. So instead of having 2 different clocks, we can just delete this thing. move some lines around, and put a not element here from the clock and connect it to the clock of general purpose register. So I go into general purpose register. Let's say I just delete. Oh, I actually can erase the contents by setting reset high and low. So at this point, register contents are empty. When I hit, for example, I change the value to something else. When I hit clock rising edge, instruction is loaded into instruction register and forwarded to instruction decoder, and it sets all the control signals. And right now, general purpose register is all zeros. And when I hit clock falling edge, it will be the rising edge for writing, and on the falling edge of master clock, the values are written into the register and the program counter. So this is how CPU works: on rising edge read instruction, on falling edge write results. Okay, so that is all for this lab, and we will do some finishing touches in the next time. But generally, this is how instruction decoder works, and almost like how all of the CPU works inside. So that's all for today.